Welcome to part 3 of Fun with Exponents. In this episode, we look at a single solution to m to the nth power equals n to the nth power. In part 1, we looked at the classic proof that you can take a rational number and raise it to a rational power and end up with an irrational number. In part 2, we turned it on its head and looked at a delightful proof that you can also take an irrational number and raise it to an irrational power and end up with a rational number. This time we'll look at the expression m to the n equals n to the m. This is a number theory question, and we're going to ask how many solutions are there to this equation. It would be trivial if we allowed m to equal n, so let's specify that m is not equal to n. And in addition, m and n should be whole numbers. That is, they're greater than 0, and they're 1, 2, 3, and so on. So our challenge is to find out how many distinct positive integers there are that satisfy m to the n equals n to the m. This delightful proof comes from a post from Keith McNulty, which you can find at this URL. Let's start with some examples of m to the n equals n to the m. For instance, 2 to the third is 8. But since 3 to the second is 9, this is not an example of where 2 to the third equals 3 to the second. M to the n does not equal n to the m. On the other hand, if we look at 2 to the fourth, 2 to the fourth is 16, and 4 to the second is also 16. So 2 to the fourth equals 4 to the second. This is a solution of m to the n equals n to the m. In fact, a little spoiler alert, 2 and 4 are the only numbers for which m to the n equals n to the m. Or more explicitly, 2 and 4 is the only pair of distinct positive integers for which m to the n equals n to the m. Let's prove it. Since both m and n are greater than 0, we can transform this equation m to the n equals n to the m by taking the log of both sides. In math, we tend to take the natural log, the log base e, and you know from your properties of logarithms that we can then bring down the exponents, so this becomes n log m equals m log n. And again, since m isn't 0 and n isn't 0, we can divide both sides by m times n, and so n log m equals m log n becomes log of m over m equals log of n over n. What does y equals log x over x look like, and what can we tell from this graph? We're only interested where x is greater than 0 and also where y is greater than 0. And so we're only interested in the portion of the graph for x greater than 1 because that's the portion for which y is greater than 0. You can see that one peak there, that one local maximum. In fact, it's a global maximum. And it looks like it falls somewhere between x equals 2 and x equals 3. In fact, if you remember your calculus, and you don't need to, we can find our local max by taking the derivative of y equals log x over x, and the derivative is 1 minus the log of x over x squared. So we'll find a critical point when this equals 0. So where does this equal 0? Again, since x is not 0, then x squared is not 0, so 1 minus log x over x squared is 0 exactly when 1 minus log x is 0. This happens when the log of x equals 1, and that happens when x is e. E is approximately 2.718. That's plenty accurate for our needs. So we've identified the x-coordinate for our max value. Let's zoom in a little bit and think about what we know. We're looking for an m to the left of e and an n to the right of e so that the y values are the same. The only two integers to the left of e are 1 and 2, and so that shows us there's only one possible m. It's got to be less than or equal to e, and it's got to be greater than 1 because the y value for 1 is 0 and y has to be greater than 0. And since m has to be an integer, that tells us that m must be 2. Really, it tells us that our only possible candidate for m is 2. So let's follow this up to our graph and draw a horizontal line looking for where else that line intersects our curve. And oh my goodness, it looks like it intersects at 4. So n equals 4 is a great candidate. Now hang on, I just drew lines on a graph. Who says that it actually hits it exactly n equals 4? So let's investigate m equals 2 and n equals 4. When n is 4, the log of 4 over 4 we can express as the log of 2 squared over 4. We can bring down the 2 in the exponent, so it's 2 log 2 over 4. And this simplifies to the log 2 over 2. So the log 2 over 2 is the same as the log 4 over 4, and we know already that 2 to the 4 is 4 squared, so we've seen that 2 and 4 are the only numbers for which m to the n equals n to the m. Or again, being a little more precise, 2 and 4 is the only pair of distinct positive integers for which m to the n is n to the m. Isn't that fun?